So excited, Wayne.
So am I. Oh, the ticket's ready.
Oh, yeah, I can see the best band in the world.
Yeah, they're so good. There's a whole chapter in here.
Yeah.
And university lecturers always talk about them.
The whole world of science just won't shut up about these guys. That's so big.
So big.
They've got their own Facebook page. That's how you tell they're famous.
That's how you tell they're famous. That's how Facebook page.
That's why we might be famous.
Yeah.
That was
I'm concerned with Christian.
Yeah. George.
Grace.
That they're pretty great, and it is
simple
harmonic motion. Absolutely, and that is that we're going to see them if they perform.
Yep. Google them. They're great.
They're good. So this is what this video is about. It's an introduction to simple harmonic motion. So Wayne, what is simple harmonic motion apart from the best band ever?
Well, very good. It's about anything that oscillates has simple harmonic motion.
Yeah.
Because when a mass is oscillating, it will have simple harmonic motion.
Well, yeah, lots of things. And actually, to think about it is it's always something going up and down, but from a different viewpoint.
Yeah. So if you have a mass attached on a spring, that will actually be going up and down.
Yeah, and you can see that will be the oscillating. If you say have a wheel going towards you, but there's a red dot in one place of the wheel. For you, it would just look like the red dot's just going up and down.
Yeah, if it's coming towards you out of the plane, as it goes around, you're just going to see it go down.
Yeah, and that's another example of simple harmonic motion.
Yeah. Pendulums going from side to side, they're oscillating. When you strum a guitar from our best band ever, there's oscillating.
Oscillating there. So oscillations are important, so you need to know some terms about oscillating and ways in general. You should be recommending them air, so if you're not...
Let's go through them.
Yes, you have amplitude.
Amplitude is the maximum displacement at any point. That's amplitude, you've heard of that. Displacement is another word in itself, and it's the distance from the equilibrium position. So the amplitude is always the maximum, that's a set thing all the way along. If you assume there's no air resistance and whatnot on the stuff.
Yeah.
Displacement does change. As the spring goes down, its displacement is changing from its equilibrium position.
Yeah.
And its amplitude will be right at the bottom of the maximum displacement.
Yeah. Then we have frequency.
Frequency is the number of oscillations per second. So it's measured in hertz, as you know.
Yeah.
And there's the period, which is the time for one oscillation.
Yeah.
And to find the frequency, you do 1 over the period. As you know, you should know all of these things.
Yeah, period is
quite hard for you to write this all very quickly.
It is quite difficult, and it to be even vaguely legible.
Things about simple harmonic you need to know is that we can say that acceleration is proportional to displacement, but we also say that the acceleration is in opposite direction to the displacement.
And these two things are very important to bear in mind, because this is when but later on we're doing graphs in a different video, it's how you can derive where the acceleration will be its greatest and stuff like that.
Yeah. So in this proportional sign I said acceleration is proportional to displacement. You have to put negative displacement because they're going in opposite directions.
So if you think about a pendulum, when it's furthest this way, it'll be accelerating that way, but its displacement is that way.
Yeah. And the same with a spring, as it goes down, you know its displacement is increasing from the equilibrium, but it's a vector, so it has a direction.
Yeah.
And it's decelerating that way, so it's accelerating upwards, so opposite direction. Now, I don't like that fish.
I don't like that fish either. So, as always, you get rid of fish with constants.
Fish hate constants.
They just can't deal with them. Special K is not a thing.
Minus K, X. The minus could be anywhere because it's being multiplied.
Yeah.
And again, we have to ask the question, what is the constant?
Well, now we haven't done many videos on this, we can't just call back on our previous knowledge, so what do we need to know, Wayne?
Well, we can just plain and simply put it, 2 pi f squared.
And this is the thing that's Wayne's put in the corner there.
And it's, you see the 2 pi, it's related to radians because it's essentially circular motion but in a plane. It's like the wheel going round represents a circle.
And for these questions to work, in general, always be in radians, especially the next bit.
Then it becomes more important, but all of this should be in radians.
So get very used to it. Yeah.
So we did speak not that long ago, a couple of videos ago, about how to get get radians to degrees.
Yeah.
But easier is just to find the setting on your calculator.
Yeah, it should be a mode, and then it will say deg, turn it to rad. But if you do want to change it, relationships.
So from this, we can get 2 very special equations. They look quite similar, and just draw one of them up in the top corner.
I have, so I'll draw it again a bit bigger here.
x, the displacement, is equal to
Ooh, wrong A.
a
Sorry.
rather than acceleration. A is the maximum displacement at any point.
Yes, that'd be the amplitude.
Sine 2 pi ft. So you can see if it's sine of this, if this is in degrees, you're going to get a very wrong answer. Just make sure it's in radians.
Yeah. There's another equation. The only difference is it's a cosine, not a sine. Now you use these two equations in different places.
You would?
So I think the easy way to again show where you use them is in a pendulum.
Yep.
So you use the sine one where you enter a lovely graph here, where you start in the middle. So you start with 0 displacement.
Yep. Think of the
You
sine
use the
graph
sine.
being plotted against x of your displacement. If
Yeah.
x is 0, this is a displacement time graph.
Yeah.
If at time equals 0, the displacement is 0, so the pendulum being here, vertically down, the equilibrium position, then you can use the sine one to work out anything you want in there. You
Yeah.
have the other things.
But your cause is different, so it will instead be a different graph, and it's where it starts at maximum displacement. So basically, when you do an experiment, when you'll be doing pendulums, you'll be holding it and then dropping it. It's from where you're holding and dropping it.
Yeah. Normally, you'll be dealing with this one unless they tell you they're dropping it from this one.
So mostly assume it's this top one, but yeah, can be both.
So let's sort of look at the sort of question we're going to get here.
All right.
So again, it's going to be some sort of pendulum question.
Okay.
Is quite common.
Yeah, pendulum springs is what I like using.
Yep. Applicable to both, except there's no angle in the spring. It's just simply the first equation.
Yeah.
A equals
So they
2 pi f squared x.
yeah, so they prepare pendulum because they are harder.
Yeah. So if we say, should we go with the worked example in the book?
I think it's a
rather
good
than
idea.
thinking of one
I'm
of.
thinking one because yeah. All right, let's try that.
Okay.
So I'll write down what we have.
We have a simple pendulum undergoing simple harmonic
Right.
motion. It's got a period of 2 seconds. That's
Okay.
the first thing they tell you. So t equals 2. And the amplitude of its movement is 15 centimetres.
Okay.
So it asks you to work out the frequency, then the maximum acceleration, and the displacement at different points. We'll go through them one by one. So part A is work out the frequency.
Okay.
Nice and simple. Frequency is 1 over the period. You should know that from your AS level with
Yep.
your waves and whatnot.
I mean, our period, so that's fine. So that just equals a half.
Or 0.5 hertz. That's nice and simple.
Yeah.
Part B, it's maximum acceleration.
Okay.
So this one's the first equation we did. We don't need to take into account angles and stuff just yet.
Okay.
Its maximum acceleration is going to occur at minus 2 pi f squared x.
All right.
But essentially we can ignore the minus, because what the minus means is...
It's in the opposite direction to the displacement.
Yeah, so really it should be a negative displacement. So then the negative makes it positive.
Yeah.
What you can just do is you can just put it into your formula.
Okay.
So we're going to have 2 pi f, which we've just worked out the frequency.
Yeah.
So it's going to be 2 times pi times 0.5, all of that squared.
Yeah, so it just says pi f squared. It's half times 2.
Ah, genius.
And
Times
then,
0.15.
yeah, you have to keep it in metres.
Yeah, careful of that.
Yeah.
And I'll just give you the answer rather than typing it into a calculator.
Yeah.
1.48 metres per second.
Okay. 1.48.
Metres per second.
Yeah. Just check.
Then it asks you to work out the displacement at 2 different times. Now this is where it gets a little bit trickier, because this is just plonking numbers into a formula. You know the frequency, you'll have this formula that's in your relationship booklet.
Yeah.
Now it gets a little bit jazzier.
So, what are our 2 times?
Our 2 times is 0.5 seconds
Okay.
and 0.25 seconds.
So the first thing I'd do is think about whereabouts in the swing it is. 'Cause it's pendulum.
Yeah. So what's happened is this pendulum's been pulled up and it's been let go of, but the timer wasn't started until it was in this equilibrium position.
Because it hasn't told us when it was started, we have to assume it's going to be our sine one, essentially.
That's what you assume in your exam.
Yeah.
Unless it tells you that the timer was started when it's at the top.
Yeah.
You've got to assume it's been dropped, so it's moving,
Mm-hmm.
but the timer started there, so at time
Yeah, so
equals
time
0 is
0,
there.
displacement equals 0. So then we need to think about what our time is. For 0.5 seconds, how far are we through our one oscillation?
So in 2 seconds, it's gone up here, it's
All the
gone
way back
back,
there.
and it's gone back to the centre.
Yeah.
Now 0.5 is a quarter
Yeah.
of 2. So how far along must it have gone? We can divide this up into sections.
Yeah.
So
So you have
one
a part
section
going
is up
up.
there,
We have a part going down,
back to the middle,
and we have a part going up, and then down again.
and it's only going to have time for one of those 4 movements.
And starting in the middle, it has to be at either end.
Yeah, it doesn't matter which way.
No.
I'm saying we've dropped it from this side. You could easily say it's dropped from the other side, but what's
Doesn't
going to
matter.
happen
It's
is
going to be
it's
a
gonna be there.
maximum displacement.
Yeah. So what's the maximum displacement? Well, it's 0.15 metres. We were
So
told there.
that is the answer. Is it in blue? That is the answer there.
Next, it gets a little more awkward because the next one is 0.25 seconds.
Okay.
That's an eighth of the way.
But you can't assume it's in the middle because it won't be uniform.
Yeah, because it's going to decelerate as it goes up here because of gravity. It's
Yeah.
going to be decelerating. So you can't just say, well, it's in the middle and half of 0.15.
Because it won't be. So now we have to use our sine equation.
Yeah.
So write that up again.
So the reason we use the sine equation, I think, is better explained with this question, is because the timer was started here. Okay, because it didn't say it was started at an angle like this. It was started at the equilibrium position. So at time equals 0, the displacement is 0. Remember, the displacement is the distance from the equilibrium. So at t0, the displacement is 0. We can apply that to the sine graph. That's how you remember.
Yeah, that's a good way to remember it. So now you have this equation.
We do.
So
A is still the maximum,
Yeah.
and we know that's 0.15 metres.
So we put that in.
At 0.15 metres, we've got the sine of, and now it has to be in radians. The
Yes,
sine
it's
of.
very important.
So 2 pi ft. Now the frequency isn't going to change regardless of how long across this you are.
Yes, it's going to be a half.
Frequency.
And our time is one we've been given.
Yep, 0.25 seconds. And what this will do, quite cleverly, is tell you the displacement from the equilibrium position at this time. So you just plonk your numbers in. I'll just
That'll
give you the
us
answer.
a value.
10.6 centimetres,
Okay.
0.106 metres if the question specified metres.
Yeah, either works.
But it's just recognising that it has to be the sine graph and just knowing what to do.
And it's not falling into the trap of saying it's just in the middle, because it won't be.
And Google simple harmonic motion.
Do it.
I'm so excited. I'm so excited. Triv was very naughty during this video. We had 2 pi f squared, and the f was a half, so the 2 and the half should cancel to get pi squared. But Triv, during the video, wrote pi f squared, which was wrong. And after the video we went, oh god, wait, I was wrong. Have you learnt your lesson now, Triv? 2 times a half is 1. He's learnt his lesson. Have you learnt your lesson? Good. Clever cracker out.